For as long as humans have existed, there has been gravity. It is the oldest of companions, present before fire, before language, before the very notion of measurement. Our ancestors felt it every moment of their lives, the invisible pull that held their feet to the ground, that made stones fall, that made rivers flow downward toward the sea. Yet because it was so constant, so unchanging, it was for millennia almost invisible to thought. No one questioned why objects fall, because they always did. It was not until much later that the human mind learned to separate the obvious from the profound, and to see that this ordinary pull was in fact the most mysterious of all the forces of nature. The earliest civilizations explained the falling of objects and the movements of the heavens as the work of gods. To the peoples of Mesopotamia, the vault of the sky was a place of divine will, and the earth below was the realm of humanity, held in its place by powers beyond comprehension. In ancient Egypt, the rising and falling of the Nile was seen as the breath of gods, yet in truth the tides that touched distant seas were already whispering the presence of gravity. The philosophers of ancient Greece began to approach the problem differently. Aristotle argued that every element had a natural place. Earth and water sought the center, which is why stones and rain fell. Fire and air sought the heavens, which is why flames leapt upward. It was a vision that explained the everyday world with a kind of elegance, but it offered no mechanism and no measurable prediction. It was philosophy more than physics, yet it shows how early minds were already struggling to make sense of what seemed obvious and yet unexplained. The sky itself provided deeper mysteries. Farmers and sailors alike observed how the tides seemed to follow the phases of the moon. This invisible link between a distant celestial body and the water rising and falling on Earth was one of the earliest clues that gravity was not just a local phenomenon, but something that connected the heavens and the Earth. Ancient astronomers carefully mapped the motions of the planets. They noticed that these wandering stars followed strange paths, sometimes moving forward, sometimes drifting backward. The very word planet comes from the Greek for wanderer. To them, the heavens were imperfect in a way that demanded explanation. In the Renaissance, the old world of Aristotle's natural places began to crumble. Copernicus dared to place the sun at the center of the cosmos, rather than the Earth. Galileo used the telescope to reveal that the moon had mountains and craters, that Jupiter had moons of its own, that the heavens were not perfect and immutable, but physical worlds, governed by the same rules as Earth. He dropped spheres from the Leaning Tower of Pisa, if not literally then at least in careful experiments, and discovered that objects of different weight fall with the same acceleration. Already the old philosophical categories were being replaced by experiments, measurements, and mathematics. Yet it was Isaac Newton who transformed gravity from an invisible habit of the world into a universal law. The story of the falling apple may be half legend, but it captures a deep truth. Newton saw that the same force that pulls an apple toward the ground also pulls the moon into its orbit around Earth, and Earth into its path around the Sunday. He gave this force a name, gravity, and he described it in an equation so simple and so powerful that it stood unchallenged for centuries. Two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. With that single insight, the falling stone, the tides of the ocean, and the dance of the planets were united under one principle. The law of universal gravitation was a revelation. For the first time, the heavens and the earth were explained by the same mathematics. The planets were not divine wanderers but predictable travelers on calculable paths. With Newton's laws, astronomers could forecast eclipses, chart the trajectories of comets, and even discover new planets such as Neptune, found because of irregularities in the orbit of Uranus that pointed to another world tugging from the darkness. Gravity was no longer just the pull of the ground, it was the architect of the solar system. And yet, even as Newton's mathematics conquered the skies, one question remained untouched. Newton himself admitted it. He had described gravity, but he had not explained it. He could calculate its effects with exquisite precision, but he did not know why it existed at all. What was this invisible tether stretching across empty space, binding masses together across vast distances? Newton confessed that he did not feign a hypothesis. He gave the universe a law, but not a reason. This silence is important. It is the difference between description and explanation, between knowing how and knowing why. For centuries, scientists were content with how. The law worked, the predictions matched, the planets kept their courses. But as our understanding deepened, the unease grew louder. Gravity seemed too instantaneous, too absolute. How could the sun hold Earth in orbit through empty space without any medium, without any delay? How could the tides on Earth respond to the moon's pull across hundreds of thousands of kilometers, as if touched by an unseen hand? Newton's genius gave humanity a framework, but it also left a void. And in that void lay the seeds of the next revolution. Because if Newton told us how gravity acts, he left us with the haunting truth that no one yet knew why it exists. The world that Newton's gravity revealed was orderly and mechanical, like a grand clockwork. Every planet was a gear, every orbit a carefully carved groove, every celestial body a piece in a vast machine governed by mathematical precision. It was a vision so powerful that it shaped the entire Enlightenment. Philosophers and scientists came to believe that nature itself was a grand mechanism, that the universe was a book written in the language of mathematics, and that to understand it was to read the mind of God. For the first time, humanity felt it had a framework capable of predicting not just tomorrow's sunrise, but the entire choreography of the heavens. The reach of Newton's laws was astonishing. Mariners could navigate the oceans by calculating the motions of the moon and the planets. Engineers could design bridges and machines with confidence that mathematics mirrored reality. Astronomers could use telescopes not just to admire the heavens, but to predict them, to say where Saturn would be years in advance, or when the next eclipse would cast its shadow. The very idea of science as prediction took root here. And yet, even in the triumph, questions lingered, like whispers in the silence of space. Newton's gravity acted instantly, no matter the distance. If the sun were to vanish this moment, Newton's equations said Earth would immediately fly free of its orbit. But how could such a signal travel infinitely fast? What medium carried it? Newton himself never pretended to know. He described gravity as an action at a distance, a phrase that satisfied no one fully. He admitted, almost with reluctance, that he had no explanation for its mechanism. He was the greatest mathematician of his age, but here he left only mystery. Still, his framework was so precise that it seemed unshakable. When the French mathematician Pierre-Simon Laplace published his Celestial Mechanics, he argued that if one could know the positions and velocities of every particle in the universe, Newton's laws would predict the future and retrodict the past with perfect clarity. For Laplace, the cosmos was a place without uncertainty, without room for chance, without hidden forces. Everything followed the chain of cause and effect dictated by the mathematics of Newtonian gravity. This vision was intoxicating. For more than 2 centuries, Newton's law of gravitation reigned supreme. Astronomers discovered Uranus and then Neptune by noticing how their orbits tugged against prediction and following the mathematics to new worlds. Edmund Halley, a friend of Newton, used the law to prove that a comet observed in the 1680s would return in 76 years. And it did, exactly on schedule, a ghostly traveler bound to the solar system by gravity's leash. Yet cracks did begin to show. Mercury's orbit, the innermost of the planets, betrayed a subtle anomaly. Its path around the Sun was not perfectly matched by Newton's equations. Each orbit, the point of closest approach, shifted slightly, an effect known as the precession of the perihelion. Astronomers tried to explain it by hypothesizing another planet, Vulcan, orbiting even closer to the Sun, but no such planet was ever found. The discrepancy remained, small but nagging, like a note out of tune in an otherwise flawless symphony. Beyond the solar system, too, Newton's vision left mysteries. Gravity reached across empty space. But what was this emptiness? If space was a void, how could it carry influence? If it was not a void, then what medium lay between the stars? Some argued for an ether, an invisible substance filling the cosmos, but no one could detect it. Others insisted the mathematics was enough, and that no mechanism was needed. For centuries, the debate remained unresolved. What Newton had given the world was both triumph and burden. He united the heavens and the earth, showed that one law governed apples and planets alike, and proved that mathematics could reveal the architecture of the cosmos. But he also left a hole at the very heart of physics, an unanswered question that would not go away. Why does gravity exist? What is the nature of this force that binds every atom of matter together across the void? The 18th and 19th centuries saw extraordinary advances in science. Electricity and magnetism were tamed into equations by Maxwell. Chemistry was formalized into the periodic table. Biology discovered the hidden patterns of inheritance through Darwin and Mendel. Yet through all this progress, gravity remained curiously untouched. Newton's formula was used as a tool, reliable and precise, but the underlying question of its origin was quietly set aside. It was as if humanity had grown comfortable with a ghost that haunted every calculation, whispering that there was more to the story. This comfort would not last forever. The small anomaly of Mercury's orbit, the troubling notion of instantaneous action at a distance, and the rise of new ideas about space and time would all eventually converge into a storm. And when that storm arrived, it would not merely adjust Newton's laws, it would overturn the very stage on which the universe played out. Newton had built the clockwork cosmos. The next revolution would reveal that the clock itself was an illusion. In the twilight of the 19th century, Newton's vision still stood tall, but its foundations had begun to tremble. The age of steam and steel believed itself to be a Newtonian age, an era of machines, engines, and predictable mechanics. Factories roared with pistons, whose motions could be calculated with precision. Railways stretched across continents, their schedules as regular as clockwork. To many, it seemed that human mastery of Newton's laws was complete, that the universe itself was a knowable mechanism, waiting only to be catalogued. But nature has a way of humbling certainty. Subtle cracks in Newton's edifice deepened with each decade. Astronomers could no longer ignore the restless orbit of Mercury, which drifted slightly out of step with prediction. Theories of a hidden planet, of unseen asteroids, failed to provide an answer. The mystery persisted, like a riddle waiting for a new kind of mind. Even more unsettling were the growing questions about space and time themselves. Newton had imagined space as a stage, an infinite arena upon which matter performed. Time flowed endlessly, a river independent of events, ticking uniformly for all. His laws required this absolute framework, and for centuries, no one dared challenge it. But experiments with light and electromagnetism began to reveal inconsistencies. Light seemed to travel at one constant speed, no matter how one moved toward or away from it, defying the rules of simple addition. The universe was whispering that the foundations of Newton's clockwork were illusions, that space and time were not what they seemed. Yet gravity remained the most stubborn mystery of all. To say that every mass attracts every other mass was not to explain, but only to describe. Why should mass pull on mass? Why should the moon feel Earth's tug across the emptiness? Newton had refused to speculate, but the silence became unbearable. By the dawn of the 20th century, it was clear that a deeper truth lay hidden, and so the stage was set for a revolution. Into this world stepped a quiet patent clerk from Bern, a man who saw not just numbers, but questions, who doubted the obvious and challenged the absolute. His name was Albert Einstein. He would take the familiar universe of space and time and bend it, showing that the very fabric of reality was not a passive stage, but an actor itself. He would show that gravity was not a force at all, but something stranger, more elegant, more profound. The story of gravity, the oldest of forces, was about to be rewritten. Newton had given humanity the law that governed the heavens, but Einstein would reveal that the heavens themselves were curved, and that gravity was nothing less than the shape of the universe. When Albert Einstein entered the stage of physics, he did not come as a conqueror, but as a questioner. He was not a professor at a grand university, nor the leader of a scientific institute. He was a young man working in a patent office in Bern, reviewing applications for electrical devices, a job that demanded precision but offered little prestige. Yet it was in this quiet routine that his imagination roamed free. He daydreamed of chasing beams of light, of sitting inside an elevator sealed off from the outside world, of watching the universe from impossible vantage points. Where others saw equations, he saw thought experiments, vivid images that bent reality in his mind's eye until it revealed its secrets. His first great insight, special relativity, redefined the relationship between space and time. No longer could time be absolute, ticking identically for all observers. No longer could space exist as a fixed, eternal backdrop. Instead, space and time fused into space-time, a four-dimensional fabric in which events were stitched together. Motion through this fabric was relative. Two observers could disagree about the duration of an event or the length of an object, and both could be correct, as long as the speed of light remained the one universal constant. But special relativity, for all its elegance, did not address gravity. Newton's law still pulled at the planets, still bent the trajectories of falling apples, still whispered across the void. Einstein knew that his vision of space-time was incomplete unless it could account for the oldest force of all. He began to search for a way to bring gravity into the heart of relativity. The key came through a simple and profound thought experiment. Imagine an elevator in deep space, far from any planet or star. If the elevator accelerates upward with constant force, the passenger inside will feel pressed to the floor, as if gravity were present. Drop a ball, and it will fall to the floor with steady acceleration. Now imagine the same elevator sitting motionless on Earth. To the passenger, the experiences are identical. There is no experiment inside the sealed chamber that can distinguish acceleration from gravity. This is the principle of equivalence, and it became Einstein's guiding light. If acceleration and gravity are the same, then perhaps gravity is not a force at all, but a kind of acceleration. But acceleration relative to what? The answer, Einstein realized, was space-time itself. Matter tells space-time how to curve, and curved space-time tells matter how to move. In this radical vision, the apple falls not because the Earth pulls it, but because Earth bends space-time, and the apple follows the natural path through that curved geometry. Planets orbit not because they are tugged by invisible strings, but because the sun shapes the very fabric around it, guiding them into elliptical paths. This idea was as bold as it was beautiful. To turn it into a theory required mathematics beyond what Einstein had at first. He immersed himself in the geometry of curved surfaces, studying the work of Gauss and Riemann, who had described how to measure distances and angles on warped spaces. Where Newton's universe was built of straight lines and absolute coordinates, Einstein's universe was pliable, dynamic, a stage that could bend and ripple. The result was the general theory of relativity, unveiled in 1915. Its equations were daunting, but their meaning was clear. Gravity was geometry. Mass and energy told space-time how to curve, and space-time curvature told matter how to move. The law of universal gravitation was not discarded, but absorbed, explained as a shadow of deeper geometry. For the first time, gravity was not merely described, but understood. Yet theories are judged not by beauty, but by evidence. Einstein's equations made predictions that could be tested, and one of them concerned Mercury's stubborn orbit. The precession of its perihelion, unexplained for centuries, emerged naturally from the curved space-time near the Sunday. Einstein had solved the riddle that Newton could not. In a single stroke, a cosmic anomaly was no longer an irritation, but a triumph. Still, Einstein needed something dramatic, something visible to all, to convince the world, and the universe soon provided the stage. Einstein's equations whispered of wonders beyond imagination, but equations alone cannot convince the world. They must be tested against the sky. One of the boldest predictions of general relativity was that light itself would bend when passing near a massive object. If space-time curves, then even the path of light, the swiftest traveler in the universe, must follow that curvature. To test this, one would need to measure the apparent positions of stars when their light passed close to the Sunday. Yet how could this be done when the sun's glare drowns out the stars completely? The answer lay in a rare alignment, a total solar eclipse, when the moon's shadow veils the sun and the hidden stars near its edge can be revealed. The opportunity came in 1919, when astronomers prepared expeditions to observe an eclipse that would sweep across parts of South America and Africa. In one of the most ambitious tests in the history of science, teams set out with delicate instruments to capture photographs of the stars in the brief darkness. Among them was the British astronomer Arthur Eddington, who believed deeply in Einstein's vision. The world was only just emerging from the devastation of the Great War, and the idea of a British scientist testing the theory of a German physicist carried symbolic weight, as well as scientific importance. As the eclipse shadow fell across the island of Principe off the coast of Africa, Eddington's instruments clicked and whirred. In the fleeting minutes of darkness, the cameras captured the stars. Near the Sunday, when the photographs were analyzed, the results were clear. The starlight had shifted, bent by the curved space-time around the sun, just as Einstein had predicted. The deflection was small, but it matched the new theory and not Newton's. Gravity was no longer a mysterious pull across space. It was the warping of space-time itself, revealed in the bending of light. News of the confirmation spread like fire. Newspapers around the world proclaimed the birth of a new physics. Headlines declared that Newton had been dethroned and that the universe itself was stranger than anyone had believed. Einstein, once an obscure patent clerk, was suddenly a figure of global renown, his face appearing in magazines, his name whispered with awe. Rarely in history has a scientific idea leapt so quickly into public imagination. Yet beyond the fame and the headlines lay a deeper transformation. The universe itself had changed. No longer could we think of space as empty and time as absolute. They were dynamic, interwoven, and alive. The planets moved not by force, but by following the curved paths of a cosmic fabric. The sun did not reach across space to tug on Earth. Instead, Earth rolled endlessly around the well of space-time carved by the sun's mass. The predictions of general relativity did not end with light bending. Time itself would slow down in a gravitational field, a phenomenon known as time dilation. Near a massive body, clocks tick more slowly. Even the passage of time is not universal but shaped by the same curvature that guides planets and light. The stronger the gravity, the slower the time. It is an idea so counterintuitive that it sounds like fantasy, yet it is now confirmed in laboratories, in satellites, orbiting Earth, and in the workings of the global positioning system that guides travelers across the world. Without Einstein's correction, the satellites would drift, and navigation would fail within hours. Another astonishing prediction was that gravity itself could ripple through space-time as waves. Just as a stone tossed into a pond sends ripples outward, massive accelerating objects could send waves through the very geometry of the cosmos. For a century, these gravitational waves remained hidden, too faint to be detected. But Einstein's mathematics was patient, and eventually, human ingenuity caught up. In 2015, a century after general relativity was born, scientists recorded the first signal of space-time itself ringing like a vast drum, caused by the collision of two black holes more than 1 billion light-years away. It was as if the universe had spoken in soundless vibration, confirming once again that Einstein's vision was right. General relativity transformed not just physics but philosophy. It revealed that reality is not fixed but malleable, that geometry is not abstract but physical, and that the cosmos is a living structure shaped by matter and energy. The universe was no longer a stage upon which matter moved. The stage and the actors were inseparable, woven into one fabric that bent, curved, and rippled. Yet in this triumph, a new question emerged, one even deeper than Newton's. If gravity is the geometry of space-time, then why does matter curve space-time at all? What is the mechanism that links energy and mass to the bending of geometry? Einstein's equations describe the relationship perfectly, but they do not explain why the universe should work this way. Just as Newton left us with action at a distance, Einstein left us with curved space-time as a given, a truth without deeper cause. The question remained, echoing into the 20th century: if gravity is geometry, what is the nature of the fabric itself? Einstein's general relativity did more than solve puzzles of Mercury's orbit or predict the bending of starlight. It unlocked a universe far stranger than anyone had imagined. In the equations lay the seeds of possibilities so radical that even Einstein himself hesitated to believe them. Among these was the idea that if enough mass were compressed into a small enough region, space-time would curve so steeply that nothing, not even light, could escape. Today, we call such objects black holes, and they are no longer speculation, but astronomical fact, revealed by telescopes and confirmed by gravitational waves. Yet in Einstein's time they seemed absurd, monsters born from mathematics that surely nature would forbid. He resisted the conclusion, but the mathematics was patient, and the universe would eventually prove it correct. General relativity also changed the way we see the cosmos as a whole. Newton's universe was eternal, infinite, and static, with stars scattered through endless space. But Einstein's equations did not allow for such stillness. The fabric of space-time could stretch or contract, expand or collapse. To avoid this, Einstein introduced a balancing term, the cosmological constant, to hold the universe steady. Yet this was a fragile compromise. When astronomers like Edwin Hubble observed that galaxies were receding from one another, it became clear that the universe was expanding. Einstein later called his constant his greatest blunder, though in truth it was less a mistake than a glimpse ahead of its time. Today, a version of it has returned in the form of dark energy, the mysterious pressure driving the accelerating expansion of the cosmos. The revolution did not end with the stars. Relativity forced physicists to rethink even the concept of time. The ticking of clocks slowed near strong gravity, and light itself redshifted as it climbed out of gravitational wells. Time was no longer universal, no longer a background parameter flowing evenly for all observers. Instead, time was woven into the same pliable fabric as space, stretching and curving with gravity. The flow of time was not a river independent of the world, but a current shaped by the very masses that floated in it. This reshaping of the cosmos was both liberating and unsettling. The Newtonian universe had been predictable, a clockwork of certainty. Einstein's universe was dynamic, pliable, filled with possibilities of expansion, collapse, horizons, and singularities. It was a stage that could twist and tear, a fabric that could ripple like water or stretch like rubber. Humanity stood not on a solid floor, but on a vast and living geometry. Yet even as relativity triumphed, a new challenge arose from the opposite direction. At the smallest scales of atoms and particles, a new theory was being born, one that spoke in the language of probabilities and quanta. Quantum mechanics described forces not as smooth geometry, but as exchanges of particles, interactions in a restless sea of uncertainty. Where relativity was continuous, quantum mechanics was granular. Where relativity was deterministic, quantum mechanics was probabilistic. Both were stunningly accurate in their domains, and both were incompatible at their core. Gravity became the battlefield where these two visions clashed. General relativity worked perfectly on cosmic scales, describing galaxies, stars, and the expansion of the universe. Quantum mechanics worked perfectly on microscopic scales, describing atoms, molecules, and the interactions that powered chemistry and electronics. But when the two theories met, as in the heart of a black hole, or the first moments after the Big Bang, the mathematics broke down. Infinity piled upon infinity, equations collapsed, and no clear picture emerged. Einstein himself sensed the tension. He admired the power of quantum theory, but distrusted its uncertainty, its claim that chance lay at the foundation of reality. He spent his later years seeking a deeper harmony, a unified theory that could reconcile gravity with quantum physics. He never found it, and the quest continues today. But the tension he revealed is one of the greatest scientific frontiers of our age. The story of gravity had shifted again. Newton had shown it as an invisible force, acting at a distance. Einstein had revealed it as geometry, the curvature of space-time itself. Yet now a deeper question loomed. If space-time is a fabric, what is it made of? Why does matter tell it to bend? And how can this smooth geometry coexist with the grainy quantum foam of the microscopic world? As the 20th century advanced, new generations of physicists took up the challenge. They began to explore geodesics, the natural paths through curved space-time, and to see that gravity was not a force, but the shape of reality itself. But even this elegant vision left unanswered the haunting question that has guided every step. Why does gravity exist at all? The revolution was not an end, but a beginning. Einstein had bent the stage of the universe, and now physicists stood at the edge of a deeper mystery, peering into the geometry of existence itself. Once Einstein had shown that gravity was not an invisible tether but the very bending of space-time, the question became how to understand motion in such a strange landscape. Newton had taught that a force pushes or pulls an object, changing its velocity. But in Einstein's universe, an object in freefall is not being forced at all. It is following the straightest possible path through a curved geometry, a path known as a geodesic. Imagine an airplane flying across Earth. To passengers staring at the flight tracker, the plane seems to curve northward as it travels from New York to London. Yet the path is in fact the shortest route across the globe, a great circle carved into the surface of the sphere. On a flat map it looks curved, but on the sphere itself, it is the straightest line possible. This is what a geodesic is, a path that looks bent in one description, but is in fact natural and straight in the geometry it inhabits. So too with gravity. The apple that falls from the branch is not being pulled by an invisible hand, but is tracing its geodesic through space-time, curved by Earth's mass. The moon orbits not because it is tugged around a circle, but because it is forever falling along a geodesic that loops endlessly around Earth. The planets circle the sun because the sun carves a well in space-time, and their natural paths curve into orbits. The beauty of this picture is that nothing mysterious is being added. Matter moves straight ahead, but straight ahead is no longer what it once was. The analogy often used is that of a heavy ball placed on a stretched rubber sheet. The ball makes a depression, and smaller marbles rolling nearby spiral inward along curved paths. To our eyes, it looks as if the marbles are being pulled toward the ball, but in truth they are simply following the contours of the surface. This image, though limited, helps us see how curvature replaces force. Yet the real world is not a two-dimensional sheet, but a four-dimensional fabric of space and time interwoven. The apple does not fall because Earth pulls it, but because Earth bends time itself, and the geodesic of the apple leads downward toward the ground. This is why astronauts floating in orbit feel weightless. It is not because there is no gravity, but because both they and their spacecraft are in free fall, following geodesics around Earth. The floor of the spacecraft does not push against their feet, so they feel no weight. To them, it is as if gravity has vanished, though in truth, gravity is what guides their orbit. This paradox dissolves once we accept that freefall is not the absence of gravity, but the purest experience of it. The astronauts are tracing spacetime's geometry, unresisted. The mathematics of geodesics explains far more than falling apples and orbiting moons. It governs the bending of light itself. When a ray of starlight passes near a massive body, it follows a geodesic through curved spacetime, and so its path appears bent. What Newton had no language to describe becomes natural once we see gravity not as a force but as geometry. Even time flows differently depending on the geodesic followed. A clock carried into a strong gravitational field will tick more slowly, its seconds stretched by the curve of spacetime. These ideas are difficult because they ask us to abandon instinct. We are used to thinking of forces as pushes and pulls, but Einstein's lesson is that the universe is deeper than instinct. Space and time are not rigid, they are supple, shaped by mass and energy. The geometry is real, it is not a metaphor. The falling of every object, the orbit of every moon, the very unfolding of the cosmos, is written in the language of geodesics. Yet, even this beautiful story leaves questions unanswered. We can describe how matter moves in curved spacetime, but why does matter curve spacetime at all? The equations of general relativity tell us the relationship, that energy and mass dictate curvature, but they do not tell us why the fabric of reality responds in this way. Geometry explains motion, but it does not explain existence. The mystery deepens, and the path leads onward. The more one contemplates Einstein's vision, the more radical it becomes. The image of a trampoline or a rubber sheet helps us picture curvature, but it is only a shadow of the real truth. For the true stage is not a surface floating in higher space. It is space-time itself, four-dimensional and complete. There is no outside into which it bends, no hidden arena where the fabric is suspended. The curvature is intrinsic. Just as a two-dimensional being living on the surface of a sphere would know of curvature by the way triangles add to more than 180 degrees, so we know of space-time's curvature by the motions of planets, the bending of light, and the slowing of clocks. The universe requires no scaffolding. It is self-contained, and its geometry is reality. This is not easy for the human mind. We are creatures evolved to throw spears and walk across planes, not to visualize four-dimensional manifolds or non-Euclidean metrics. We reach for analogies like balls on sheets because they are tangible, but in truth, they are approximations, useful but misleading if taken too literally. In reality, the Earth does not sit upon a sheet. The sun does not sag into an invisible trampoline. Instead, mass and energy alter the relationships between events in space-time, changing what it means for two objects to be at rest or in motion, what it means for light to travel in a straight line. Geometry itself becomes dynamical, sculpted by what it contains. Think of the simplest example: a beam of light traveling from one star to another. In Newton's cosmos, light would move in a straight line through absolute space. In Einstein's, the path is still straight, but straightness itself has been redefined. In the presence of mass, the geodesics curve, so the light's straight path bends when viewed from afar. To the light, nothing unusual has happened. To us, its journey is deflected. Straightness is no longer absolute, but relative to the geometry. This subtlety matters because it transforms how we think about forces. In Newton's mechanics, gravity was a force distinct from others, acting at a distance. In Einstein's mechanics, there is no such force. There is only the geometry, and objects in freefall are not accelerated by an external push, but are obeying the simplest law of motion, to move straight ahead. What we call gravitational acceleration is merely the difference between freefall and being held up. The apple clings to the branch until the stem snaps, at which point it follows its geodesic. We feel weight not because gravity presses us down, but because the ground resists our natural path. This inversion is subtle, but profound. When you stand still on Earth's surface, you are in fact the one being accelerated. The floor pushes upward, preventing you from following your geodesic into the planet's center. You feel this push as weight. The astronaut drifting in orbit feels nothing because no surface interrupts the geodesic. In a sense, weight is not a measure of gravity, but of resistance to it. This is the equivalence principle made tangible in our bodies every day. Once this perspective takes hold, the universe transforms. The path of every planet is a geodesic carved in the fabric of space-time. The swirl of galaxies, the spiral of comets, the fall of meteors, the flow of time near a black hole, all are simply the unfolding of geometry. The cosmos becomes less like a machine of forces and more like a tapestry of shapes. Yet this picture also raises deeper puzzles. If space-time is real and malleable, what is it? Is it a substance, an ether, reborn under a new name? Or is it purely relational, a set of connections between events with no independent existence? Einstein himself wrestled with this, sometimes speaking of space-time as if it were a real medium, sometimes insisting it was only the structure revealed by relations among matter. The ambiguity remains, and beyond this lies an even sharper mystery. The mathematics of general relativity is silent about why mass and energy curve space-time. The equations declare that they do, but they do not reveal a mechanism. It is as if the fabric listens and obeys, reshaping itself according to the presence of matter. But why should reality have such pliability? Why should geometry care about energy? It is a question as deep as Newton's action at a distance, and it remains unanswered. The geometry of the universe is not merely a new description of gravity, it is a new ontology, a new vision of what existence itself is made of. Space and time are no longer the empty arena of events, but the very stage that bends, stretches, and responds. The actors and the stage are inseparable, woven together in a single whole. To understand gravity is to understand geometry, and to understand geometry is to begin glimpsing the very fabric of being. The consequences of Einstein's geometry were staggering. Once physicists accepted that mass and energy bend spacetime, they began to explore the extremes of this bending. The equations did not merely allow for slight curves around planets and stars. They permitted far more radical possibilities, places where the geometry itself folded in ways that defied ordinary experience. At first, these seemed like mathematical curiosities, abstract solutions to equations. But over the decades, they revealed themselves as real features of the universe. One of these was the black hole. When enough mass is compressed into a small enough volume, the curvature becomes so steep that all geodesics lead inward. Even light, the fastest traveler, cannot escape. To an external observer, time itself slows near the edge of such a region, freezing as it approaches the horizon of no return. At the center lurks a singularity, a point where the known laws of physics collapse. Black holes are the ultimate testament to geometry as reality. They are not made of ordinary matter in the way stars are, but of spacetime itself bent into a trap. What was once thought impossible has now been photographed, its shadow etched against the glow of surrounding gas. Another was the expansion of the cosmos. In Newton's view, an infinite universe could remain static, each star held in place by a delicate balance of forces. But Einstein's equations said otherwise. A static solution was unstable. The fabric itself must stretch or contract. At first, Einstein resisted this, adding the cosmological constant to preserve stillness. Later, when astronomers observed galaxies receding in every direction, he admitted that the expansion was real. What had begun as geometry near the sun had become a description of the entire universe, a fabric stretching like the surface of an inflating balloon, carrying galaxies apart. These revelations transformed cosmology into a science grounded in relativity. The Big Bang was not merely an explosion of matter, but an expansion of space-time itself. The future of the universe, whether to expand forever or collapse back into itself, became a question of geometry and energy. Even the mysterious dark energy that drives accelerated expansion today is understood through Einstein's framework, a pressure of the fabric itself. The geometry also reshaped how we think about time. Near strong gravity, time slows. Two twins, one on Earth and one near a black hole, would age at different rates. This is not illusion but fact, confirmed by experiments with atomic clocks flown on airplanes and satellites. Time is elastic, stretched by curvature. The arrow of existence itself is bound to gravity. The philosophical impact was no less profound. The universe was no longer a stage built once and for all. It was a living geometry, evolving, rippling, and stretching. The Earth does not orbit because of a force pulling it, but because it is sliding endlessly along a geodesic carved by the sunday. Every star, every galaxy, every photon of light is a thread woven into the curvature of reality. To live in such a universe is to live inside a fabric that shapes every heartbeat and every orbit. And yet, even as general relativity explains so much, it left the haunting question unsolved. Why does matter curve space-time? Why should energy dictate geometry? Einstein's equations are silent on the mechanism. They are descriptive, not explanatory. They tell us how curvature and mass are related, but not why the relation exists. The mystery of gravity is not erased, only reframed. The question shifts from how masses attract to why the fabric of space-time is pliable at all. This is where the elegance of geometry begins to strain against the quantum world. For while relativity paints a smooth, continuous fabric, quantum mechanics insists that at the smallest scales, the universe is granular, jittering with fluctuations, uncertain and probabilistic. The geometry of relativity and the discreteness of quantum theory do not easily coexist. At the boundary where they must meet, in the heart of a black hole, or the instant of the Big Bang, the mathematics shatters into infinities. And so, even as Einstein's theory reigns over the stars and the galaxies, physicists know it is incomplete. It must one day be joined with quantum physics in a deeper synthesis. The geometry of the universe explains gravity with breathtaking power, but it also points toward a deeper layer not yet understood. The next chapter in the story begins here. If geometry is not enough, perhaps gravity itself must be quantized, described not as smooth curvature, but as particles and fields. The search for a quantum explanation of gravity begins with this realization that the stage Einstein revealed, beautiful as it is, may not be the final truth. By the middle of the 20th century, Einstein's revolution had remade the cosmos. Space and time were no longer absolute. Gravity was no longer a force, but the curvature of space-time. Yet even as general relativity triumphed, another revolution was unfolding, one just as profound, and its language was entirely different. This was the rise of quantum mechanics, a theory that described the smallest scales of nature, not with smooth curves, but with discrete quanta, probabilities, and uncertainty. Quantum mechanics began with the riddle of light itself. Was it a wave or a particle? The experiments said it was both. Then came the atom, once thought indivisible, revealed as a nucleus surrounded by electrons that could occupy only discrete energy levels, jumping from one to another with bursts of radiation. The mathematics of quantum theory predicted these jumps with stunning accuracy, even as it defied intuition. At its heart was uncertainty. One could never know both the position and the momentum of a particle with absolute precision. The world was not clockwork but probabilistic, a haze of possibilities that only became definite when measured. Soon, this framework expanded into quantum field theory, in which every particle was understood as an excitation of an underlying field. The electron was a ripple in the electron field. Photons were ripples in the electromagnetic field. Forces were mediated not by invisible pulls but by the exchange of particles. Electromagnetism was carried by photons. The strong force was carried by gluons. The weak force by W and Z bosons. Every interaction in nature, except gravity, found its place in this quantum language. It was natural to ask whether gravity too could be described in this way. If all other forces were mediated by particles, perhaps gravity was as well. The hypothetical quantum of gravity was named the graviton, a massless, spin-2 particle that would carry the interaction just as the photon carries electromagnetism. In this picture, two masses attract because they exchange gravitons, invisible messengers flitting between them. The idea was elegant, but it carried a problem. Unlike photons or gluons, gravitons would be nearly impossible to detect. Gravity is by far the weakest of the fundamental interactions. A simple refrigerator magnet can lift a paperclip against the entire pull of Earth. To observe a single graviton directly would require a detector so massive and sensitive that it would collapse into a black hole under its own weight. In practice, gravitons may remain forever hidden. Worse still, the mathematics of quantum gravity resisted every attempt at consistency. When physicists tried to quantize space-time the way they had quantized electromagnetism, infinities multiplied uncontrollably. The equations produced nonsense results, divergences that could not be renormalized away. Quantum field theory, so successful elsewhere, broke apart in the face of gravity. Here lay a profound tension. General relativity described the universe on the largest scales with astonishing accuracy. Quantum mechanics described the universe on the smallest scales with equal brilliance. But when the two were brought together, the harmony collapsed. At the heart of a black hole or in the first instant of the Big Bang, both theories should apply, yet they gave contradictory answers. Relativity insisted on smooth geometry. Quantum mechanics insisted on fluctuations and discreteness. Reality could not obey both without a deeper, unifying framework. Physicists began to search for alternatives. Could space-time itself be emergent, a phenomenon arising from something more fundamental? Could gravity be only an approximation, a shadow cast by deeper quantum laws? Or was there truly a graviton, waiting to be revealed indirectly, perhaps in the polarization patterns of primordial gravitational waves from the birth of the cosmos? The failure to quantize gravity was more than a technical nuisance. It was a clue, a whisper from the universe that gravity might not be like the other forces at all. Perhaps it is not fundamental but emergent. Perhaps the geometry Einstein described is not the final layer, but the surface of a deeper reality still hidden from us. The search for a quantum explanation of gravity is one of the greatest quests in modern physics. It is a quest that has lasted for decades, one that has forced physicists to question not just their equations, but their assumptions about space, time, and reality itself. The quest to reconcile gravity with the quantum world led physicists down strange and daring paths. One of the most ambitious was string theory, an idea that began modestly as an attempt to explain the strong nuclear force, but soon grew into a candidate for a theory of everything. In string theory, the fundamental building blocks of the universe are not point particles, but tiny vibrating strings, so small that no microscope could ever hope to see them directly. Each vibration mode of a string corresponds to a particle. One vibration gives rise to the electron, another to the photon, another to the gluon, and hidden among these vibrations is a mode that behaves exactly like a graviton. In this way, string theory did what ordinary quantum field theory could not. It included gravity naturally, not as an afterthought, but as an unavoidable consequence. But string theory came at a price. It required extra dimensions, not the familiar 3 of space and 1 of time, but as many as 10 or 11 dimensions, curled up into shapes too tiny to perceive. It offered a rich mathematical landscape, yet it lacked definitive experimental predictions. No accelerator could probe the scales where strings vibrate. The theory became a world of thought experiments, of abstract equations, of conjectures like the holographic principle and ADS-CFT duality, which suggested that a universe with gravity might be equivalent to a universe without it living on a boundary. These ideas dazzled with beauty, but they offered no simple test to confirm or refute them. Others turned to different visions. Loop quantum gravity sought to quantize space-time itself, breaking the smooth fabric of general relativity into discrete loops. In this picture, geometry is granular, built from tiny quanta of area and volume. Space itself becomes a weave, like a fabric woven from microscopic threads. Time too may emerge from transitions between these states. Loop quantum gravity is elegant in its minimalism, avoiding extra dimensions, but it remains incomplete. It struggles to reproduce the richness of particle physics that string theory embraces. There are other approaches as well. Causal dynamical triangulations attempt to build space-time from fundamental building blocks shaped like simplices, tiny triangles, and tetrahedra, letting the geometry grow from simple pieces. Asymptotic safety seeks to tame the infinities of quantum gravity by finding a fixed point in the mathematics where the theory becomes well-behaved. Each approach offers glimpses of a solution, yet none commands consensus. Why is gravity so resistant? Perhaps because it is qualitatively different from the other forces. Electromagnetism and the nuclear forces act within space-time, but gravity is space-time. To quantize gravity is not to add another force, but to quantize the stage itself. The actors are part of the play, but gravity is the theater, the script, the lighting. To put the stage on the same level as the actors may be, to misunderstand the play entirely. The stakes are high. Without quantum gravity, we cannot know what happens at the singularity of a black hole. We cannot understand the first moments of the universe, when densities and energies reached extremes, where relativity and quantum theory must both apply. We cannot explain why space and time exist at all, or whether they are fundamental or emergent. Some physicists hope that evidence might come from the sky. If primordial gravitational waves exist, ripples frozen from the birth of the cosmos, their patterns in the cosmic microwave background might reveal quantum features. If black holes evaporate through Hawking radiation, as quantum field theory suggests, perhaps we could learn about the underlying quantum structure of space-time. Yet these signals are faint, elusive, and perhaps forever out of reach. For now, the graviton remains a ghost, string theory remains untested, and loop quantum gravity remains incomplete. The search for a quantum explanation of gravity is not only a scientific challenge, but a philosophical one. It forces us to ask what it means for reality to be smooth or discrete, continuous or granular. It forces us to question whether space and time are truly fundamental, or whether they are shadows cast by something deeper, patterns emerging from a realm we cannot yet imagine. The mystery deepens, but so too does the sense of wonder. Gravity, the most obvious of forces, has led us from falling apples to warped spacetime, and now into the frontier where geometry and quantum rules collide. The search is not only for a theory but for a new way of thinking, one that may change our understanding of existence itself. The search for quantum gravity has always been shadowed by one central obstacle. Gravity is unimaginably weak compared to the other forces of nature. A simple magnet that fits in your pocket can lift a nail against the pull of the entire Earth. In particle physics laboratories, the electromagnetic force and the nuclear forces dominate interactions. Gravity is so feeble that at the scale of atoms it is effectively non-existent. To measure the effect of a single graviton, the hypothetical particle of gravity, one would need a detector so large and sensitive that its very mass would cause it to collapse into a black hole. The very act of trying to catch the graviton destroys the possibility of success. This difficulty makes gravity unique among the forces. For electromagnetism, we have particle accelerators and detectors that capture the showers of photons. For the strong and weak forces, we see gluons and W and Z bosons in the collisions of protons at colossal energies. But for gravity, direct detection is a dream beyond reach. The best we can do is indirect. When two black holes collide, they release energy in gravitational waves, ripples of spacetime itself. In 2015, the LIGO Observatory captured such a signal, the faint stretching and squeezing of space caused by an event more than 1 billion light-years away. This was a triumph, a confirmation that spacetime is not rigid but can vibrate. Yet even this was the classical side of gravity, the smooth waves of Einstein's geometry. It was not the quantum grain of the graviton. That grain remains hidden. Black holes sharpen the puzzle further. According to general relativity, nothing can escape them. According to quantum theory, no information can be destroyed. When Stephen Hawking showed that black holes should radiate faintly, slowly evaporating through quantum effects, he revealed a paradox. If black holes evaporate completely, what happens to the information about everything that fell in? If it vanishes, quantum mechanics is broken. If it remains, then somehow the smooth geometry of relativity must encode and release it. The clash between these two principles, the information paradox, is one of the deepest conflicts in physics. Physicists have tried to resolve the paradox with daring ideas. Perhaps the horizon of a black hole is not smooth, but a firewall, a blazing boundary that burns information out. Perhaps the interior is connected to the exterior by hidden wormholes, bridges through space-time that preserve the data. Perhaps the holographic principle is true, and everything that falls into a black hole is encoded on its surface, stored like bits on a cosmic screen. Each of these ideas reshapes our view of space, time, and gravity itself. What is striking is how gravity refuses to yield. With every attempt to fit it into the quantum framework, it slips away, forcing us to ask whether we have misunderstood it at a fundamental level. Maybe gravity is not a force to be quantized. Maybe space-time is not primary at all. Maybe the geometry we see is an emergent pattern, like the surface of water that feels smooth, but is made of countless molecules underneath. The dream of a graviton drifting invisibly through space-time might be replaced by something stranger, a vision where space-time itself emerges from entanglement, from information, from quantum connections too deep for current mathematics to express. In this view, gravity is not fundamental. It is a side effect, the shadow of something more basic, and so the chapter closes with uncertainty. The search for a quantum explanation of gravity has given us strings, loops, holograms, and paradoxes, but not yet an answer. The falling of an apple is understood better than ever, yet the reason gravity exists at all remains a mystery. The quest continues, and in the next turn of the journey, physicists ask a bolder question still. If gravity resists quantization, could it be because it is not a fundamental force at all, but an emergent phenomenon? Could the fabric of space-time itself be woven from something else? The possibility that gravity is emergent is not the end of science, but the beginning of a deeper revolution, one that takes us beyond Einstein, beyond quanta, into a realm where the very meaning of reality must be reconsidered. By the late 20th century, Many physicists had grown uneasy with the stalemate between relativity and quantum theory. The two greatest frameworks of science stood side by side, each dazzling in its success, each refusing to merge with the other. For every other force, the quantum picture worked. For gravity, it failed. The harder physicists tried to capture it, the more it slipped through their grasp. Some began to suspect that perhaps the failure was not in the mathematics, but in the question itself. What if gravity was never meant to be fundamental? What if it was emergent, a byproduct of something deeper? The clue came from an unlikely place: black holes. In general relativity, a black hole is a region from which nothing escapes. Its defining feature is the event horizon, the invisible boundary separating the interior from the outside universe. Cross the horizon, and no signal can ever return. To a classical physicist, this was the end of the story. But quantum theory refuses to stay silent. When Stephen Hawking applied quantum field theory to black holes in the 1970s, he discovered that they must emit radiation. Virtual particles, flickering into existence near the horizon, can separate, with one falling in and the other escaping. To an outside observer, the black hole glows faintly, and over immense timescales, it evaporates. This revelation carried a shock. If black holes radiate, then they have a temperature. If they have a temperature, then they must also have entropy. And entropy is a measure of information, the number of microscopic states hidden beneath a macroscopic surface. The entropy of a black hole turned out to be proportional not to its volume, as one might expect, but to the area of its horizon. This was the famous Bekenstein-Hawking entropy, written in an equation that linked gravity, thermodynamics, and quantum theory in one stroke. Why should the entropy of a black hole be tied to its surface? The answer hinted at something profound. Perhaps space-time itself stores information on boundaries. Perhaps the interior is encoded not in the volume but on the surface that encloses it. This idea grew into the holographic principle, the suggestion that the three-dimensional world we inhabit may be like a hologram, a projection from information written on lower dimensional boundaries. In such a picture, gravity and space-time themselves might be emergent phenomena born from the bookkeeping of information and entropy. To grasp this, consider how temperature and pressure emerge in ordinary matter. No single molecule has a temperature. Temperature arises from the collective motion of countless molecules, from the statistics of large numbers. Pressure, too, is emergent, a macroscopic description of microscopic chaos. Could gravity be the same? Could it be that no single quantum of reality contains gravity, but when vast numbers of quanta are entangled, when information is organized in particular ways, gravity appears as the large-scale effect? In recent decades, researchers have pursued this line of thought with growing seriousness. They have asked whether Einstein's equations themselves could be derived from thermodynamic principles, as if the bending of space-time were the statistical behavior of hidden microscopic degrees of freedom. Remarkably, in some cases this has been shown. The elegant equations of general relativity can emerge as equations of state, describing the collective behavior of underlying information. Gravity, in this view, is like elasticity, an emergent property of a material that is not fundamental, but arises from deeper structure. This perspective reframes the entire mystery. The failure to quantize gravity may not be a flaw in our mathematics, but a sign that gravity is not a particle-mediated force at all. Just as we do not look for a fundamental quantum of temperature, we may not need a graviton. Instead, we should be looking for the microscopic structure whose collective behavior manifests as space-time and gravity. The implications are staggering. If gravity is emergent, then the geometry Einstein described is not the bedrock of reality, but a surface appearance. Beneath it lies something more fundamental, perhaps quantum entanglement itself, weaving connections that, when viewed from afar, look like space-time curvature. Gravity, in this daring vision, is the side effect of information flowing, entropy balancing, and correlations knitting reality together. The question once asked of Newton, why does gravity exist, is thus turned upside down. Perhaps it does not exist in the way we imagined. Perhaps it is not a force but a mirage, a large-scale phenomenon that emerges only when countless microscopic processes combine. Like the shimmer of heat rising from a road, it is real, measurable, undeniable, and yet not fundamental. The idea that gravity might be emergent turns the universe inside out. To think that space-time itself is not fundamental, but a projection of something deeper, is unsettling. Yet the evidence points in this direction, with surprising insistence. The holographic principle stands as one of the boldest clues. Imagine a black hole once more. The Bekenstein-Hawking entropy tells us that the maximum information hidden within the black hole is proportional to the surface area of its horizon, not the volume inside. This is not just a curious coincidence. It suggests that the fundamental degrees of freedom of the universe are not stored throughout space, but rather encoded on surfaces. The interior may be nothing more than a reconstruction, a holographic illusion built from the information on the boundary. This radical vision was sharpened by the discovery of the ADS-CFT correspondence. In this mathematical framework, a universe with gravity in a higher dimensional space can be exactly equivalent to a quantum field theory, without gravity living on its lower dimensional boundary. In other words, the physics of a bulk spacetime emerges from the quantum dynamics of a boundary surface. This duality does not merely hint, but demonstrates, in a precise way, that gravity and spacetime geometry can be emergent. Though our own universe is not the special anti-de Sitter space where the mathematics works cleanly, the lesson is too striking to ignore. In this light, the failure to detect gravitons is not surprising. If gravity is not fundamental, then there may be no particle of gravity to detect. Instead, what we perceive as gravitational attraction could be the statistical manifestation of hidden quantum information. Just as temperature is not carried by a particle but arises from the average motion of molecules, gravity may arise from the collective behavior of quantum entanglement. Black hole thermodynamics deepens this suspicion. Hawking radiation implies that black holes evaporate, shrinking as they emit quantum particles. Yet their entropy, proportional to horizon area, decreases as well. How can this be reconciled with the fundamental law that entropy must increase? The answer seems to be that the missing entropy is balanced by the information encoded on the horizon. This hints that the horizon is not a mere boundary, but an active storehouse of information, a place where quantum data is written in Planck-scale units of area. Such reasoning has led physicists to wonder whether the entire universe functions in the same way. Perhaps the cosmos itself is a vast hologram, with every event we experience projected from data inscribed on a boundary beyond our perception. To us, the three-dimensional world feels solid and continuous, yet beneath it may lie a two-dimensional ledger of information. Gravity, in this story, is the way that holographic encoding manifests as geometry. The idea is intoxicating, but it is also sobering. If gravity is emergent, then Einstein's equations are not fundamental laws but effective ones, valid only at scales where the emergent description holds. Beneath them lies something more primal, something not yet fully glimpsed. The smooth fabric of spacetime might be like the calm surface of an ocean, beneath which quantum turbulence rages. Some physicists have gone further, attempting to derive Newton's law of gravity itself as an entropic force. In this approach, the attraction between masses arises because systems naturally maximize entropy. When matter shifts position, the entropy of underlying microscopic degrees of freedom changes, and this manifests macroscopically as a force, the force we call gravity. Though still controversial, such attempts show the growing willingness to treat gravity as thermodynamic rather than fundamental. To think of gravity in this way is to reimagine the universe. What we feel as weight, what binds the planets, what shapes galaxies, may not be a primary interaction at all, but the echo of information, seeking balance. The cosmos becomes not just a stage of geometry, but a computation, a vast network of entangled quantum-weaving reality from the bottom up. And yet, even this bold vision leaves questions. If space-time and gravity emerge from entanglement, then what exactly is being entangled? What are the microscopic units of information that form the substrate of the universe? We do not yet know, but the hints are tantalizing enough that physicists now suspect that the answer to why gravity exists lies not in particles or forces, but in the hidden architecture of information itself. If gravity is truly emergent, then the deepest mystery is not why masses attract, but why the universe is woven from information at all. The thermodynamic parallels are striking. Entropy drives heat to flow from hot to cold, molecules to spread out, and order to dissolve into disorder. In the same way, entropy may drive space-time itself to curve, guiding matter into orbits, collapsing gas into stars, and shaping galaxies. Gravity, in this view, is entropy's shadow written large across the cosmos. The black hole remains the most compelling laboratory for these ideas. The fact that its entropy scales with surface area rather than volume suggests that space-time cannot be what it seems. If the interior of a black hole is fully described by data encoded on its horizon, then perhaps the entire universe works the same way. In that case, the fabric of space-time is not a pre-existing stage, but a reconstruction, an emergent description created from quantum information stored elsewhere. Our experience of living inside 3 dimensions of space, and one of time, could be the illusion of a hologram. This perspective turns the question of Newton upside down. He asked why bodies attract each other. Einstein showed that they do not attract but follow curves in space-time. Now the question becomes why space-time itself should exist. If it is emergent, then gravity is not a fundamental force, but a macroscopic phenomenon, like elasticity or pressure. Just as the bending of a beam of steel is not fundamental but the collective effect of countless atoms, so the bending of space-time might be the collective effect of hidden quantum correlations. Hints of this connection come from the study of quantum entanglement. Entanglement binds particles together so that their states cannot be described independently, no matter how far apart they are. The mathematics of entanglement turns out to resemble the mathematics of space-time geometry. In some models, the structure of entanglement networks can reproduce the curvature of space-time. If this is true, then space-time itself may be woven from entanglement, and gravity may be nothing more than the manifestation of how entanglement organizes information. The boldest conjectures go even further. They suggest that wormholes, bridges through space-time, may be nothing more than entangled particles seen from a different perspective. If so, then the very connectivity of the cosmos may be quantum at its root, with space-time arising as the large-scale expression of microscopic entanglement. Gravity, in this astonishing picture, is not an independent entity, but a byproduct of the quantum threads that tie reality together. If this is true, then the quest for a quantum theory of gravity is not about finding the graviton or quantizing space-time directly. It is about uncovering the quantum information structure from which space-time emerges. It is about understanding how entanglement builds geometry, how entropy drives curvature, and how the cosmos arises as the collective computation of countless microscopic quanta. This is not yet proven. It remains speculative, tantalizing, incomplete, but the pieces fit together with suggestive elegance, enough that many physicists now take seriously the idea that gravity is not fundamental. If gravity is emergent, then the universe we inhabit is not what it seems. The weight we feel, the orbits of planets, the bending of light, the slowing of time, all may be side effects of something deeper. The story of gravity has now led us from falling apples to warped space-time, and from warped space-time to entropy and holograms. But the journey is not finished. The next step is to look directly at entanglement itself, to ask whether the threads of quantum connection are in fact the fabric of space-time. If so, then the mystery of gravity will not be solved by finding a particle, but by understanding how information knits the universe together. Quantum entanglement is one of the strangest discoveries of the 20th century. When 2 particles become entangled, their states are no longer independent. Measure one, and the other is determined instantly, no matter how far apart they are. Einstein himself called this spooky action at a distance, doubting that such a thing could be real. Yet decades of experiments have shown that island entanglement is not a trick or a flaw in our mathematics. It is a fundamental feature of reality. For most of physics, entanglement seemed like a curiosity, important in quantum information, but not central to the structure of the universe. But as the puzzles of gravity deepened, physicists began to suspect that entanglement might be more than a detail. It might be the very threads from which space-time is woven. The boldest step came with the conjecture known as ER equals EPR. ER refers to Einstein and Rosen, who in the 1930s described wormholes, tunnels, connecting distant regions of space-time. EPR refers to Einstein, Podolsky, and Rosen, who in the same decade published their famous paper questioning the completeness of quantum mechanics, the paper that introduced the paradox of entanglement. Decades later, some physicists suggested that these two ideas might be the same. Every entangled pair of particles, no matter how distant, could be connected by a microscopic wormhole. The wormholes are not passages we can travel through. They are threads of geometry, invisible yet real, that correspond to the invisible connections of entanglement. In this vision, space-time itself is nothing more than an immense web of entanglement, with gravity as its emergent shape. If true, this would explain why space-time behaves like a hologram. The correlations of entanglement carry information, and when seen on a large scale, this information manifests as geometry. The smooth fabric of space-time, the curves and geodesics of Einstein's equations, are the macroscopic expression of countless quantum threads linking particles across the cosmos. The universe we experience would then be the large-scale shadow of a vast network of quantum connections. The mathematics supports this more than one might expect. In certain toy models, the entanglement between regions of a quantum system maps directly onto the curvature of an emergent space-time. More entanglement corresponds to stronger connectivity, like stitching fabric tighter. Less entanglement corresponds to weaker connectivity, like frayed threads. Remove entanglement altogether, and the space-time disintegrates. In this way, space-time is not the stage upon which entanglement occurs. It is the tapestry woven by entanglement itself. The implications are profound. If space-time is built from entanglement, then gravity is not a fundamental interaction, but the natural consequence of how entanglement organizes information. Planets orbit, light bends, and time slows, not because there is a force or a graviton, but because the network of entanglement gives rise to curvature. The geometry is the physics of information. This picture also reframes the paradoxes of black holes. If the interior is connected to the exterior by entanglement, then perhaps the information that falls in is never truly lost. It is encoded in the entangled structure of the horizon, stored and preserved, waiting to be released through Hawking radiation or through the deeper connectivity of wormholes that cannot be traversed, but can exist as threads of geometry. ER equals EPR offers a way to reconcile quantum mechanics with relativity, not by forcing one to bend to the other, but by revealing that they are two sides of the same coin. It is an audacious vision, and it is not yet proven, but it has shifted the conversation. No longer is the question merely how to quantize gravity. The question is whether gravity and spacetime are emergent, woven from entanglement, and whether the quantum world already contains the seeds of the geometry we see. The boundary between physics and philosophy blurs here, for to say that reality is entanglement is to say that the deepest level of being is not substance, but connection. The universe then may not be made of matter and forces at its core. It may be made of information, entanglement, and relationships. Gravity would be the story these relationships tell when read on a cosmic scale. If space-time is woven from entanglement, then the smooth geometry described by Einstein is a kind of mirage, a large-scale appearance of something far stranger underneath. At the microscopic level, the universe may look nothing like space and time as we know them. Instead, it may resemble a vast web of correlations, a network of quantum states bound together by entanglement. When seen from afar, the patterns of this web appear to us as dimensions, distances, and curvature. Gravity is not an added force within this picture. It is the shape of the web itself. This idea has been tested in the only arena where mathematics offers us a clear path: the holographic models inspired by ADS-CFT correspondence. In these models, the amount of entanglement between regions of the boundary quantum system directly determines the connectivity of the emergent spacetime. Entanglement is not an accessory. It is the glue that holds spacetime together. Remove entanglement, and the geometry falls apart. Increase it, and the geometry grows smoother and more connected. The very metric of spacetime, the ruler by which distances and times are measured, is determined by the structure of quantum entanglement. The holographic principle offers a dramatic rethinking of reality. A two-dimensional surface can encode the full physics of a three-dimensional interior. Like a holographic image etched on glass, the lower dimensional information contains all the details needed to reconstruct a higher dimensional world. If our own universe is holographic, then what we perceive as three-dimensional space and flowing time is a projection from quantum data stored on a cosmic boundary beyond our reach. What feels like depth is actually encoded on a surface. Entanglement is the mechanism by which this projection gains its solidity. Without it, the world would disintegrate into disconnected fragments. With it, we experience continuity, causality, and geometry. In this view, the most intimate structure of reality is not matter, but information, not particles, but correlations. The black hole paradox once again illuminates this idea. When information falls into a black hole, it seems lost behind the horizon. But if the horizon is itself an entangled surface encoding the interior, then the information is not lost at all. It is preserved in the structure of entanglement. Hawking radiation, faint though it may be, can then carry away this encoded data. The paradox dissolves once space-time is recognized as entanglement's shadow. Even time itself may be emergent. In quantum systems, entanglement patterns can evolve, and from this evolution, one can reconstruct a sense of temporal flow. What we call the arrow of time may arise from the growth of entanglement, from the increase of correlations as systems interact. The past is the record of entanglement already established. The future is the unfolding of new entanglements yet to form. Gravity and time, inseparable in relativity, may both be consequences of information spreading across the cosmic web. To accept this is to invert centuries of intuition. We once thought matter was fundamental, then forces, then fields. Now the suggestion is that neither matter, nor forces, nor fields are ultimate. The foundation may be quantum entanglement, an invisible structure that cannot be touched or seen, but can be measured through its consequences. The bending of light, the orbits of planets, the slowing of clocks, all may be the emergent behavior of entangled information. This picture carries a kind of poetic inevitability. If the universe is information, then gravity is the grammar by which that information is organized. Space and time are the sentences written by entanglement. The cosmos is not built of things but of relationships, and the relationships themselves create the appearance of a stage upon which things exist. And yet, for all its elegance, the idea is still unproven. Experiments that could confirm space-time as entanglement are beyond our current reach. We cannot probe the Planck scale directly, cannot yet observe the stitching of the quantum web. What we have are mathematical correspondences, suggestive clues, and paradoxes that seem to dissolve when entanglement is made central. It is a theory in search of evidence, and yet it is one of the most compelling directions in modern physics. If true, it would mean that the question, why does gravity exist, has a startling answer. Gravity exists because entanglement exists. Without entanglement, there would be no space-time. Without space-time, there would be no gravity. The cosmos itself would unravel into a meaningless collection of quantum states. Gravity is not fundamental. It is the side effect of the universe being woven together by quantum threads. The suggestion that space-time is woven from entanglement forces us to confront a radical thought. What if reality is not made of things but of connections? In such a universe, the notion of empty space is an illusion. Even in a vacuum, entanglement persists, invisible threads binding distant regions of the cosmos. Remove those threads, and the fabric itself unravels. Space is not a container, it is the pattern of correlations. This perspective also reframes the great puzzles of cosmology. Why does the universe expand as it does? Why does dark energy accelerate that expansion? If space-time is emergent, then these questions may be answered not by forces acting on a stage, but by changes in the entanglement pattern that generates the stage. The geometry of the cosmos could be the large-scale reflection of entanglement networks evolving beneath our awareness. Dark energy might be not a mysterious fluid, but a property of information itself, a pressure exerted by the deep structure of entanglement. The same reasoning applies to dark matter. For decades, astronomers have seen galaxies rotate faster than their visible mass should allow. The usual solution is to posit unseen matter providing extra gravity. But if gravity is emergent, then perhaps the anomaly is not matter at all. Perhaps it is the way entanglement knits space-time in those regions. Gravity would then be not a simple law, but a reflection of deeper information, sensitive to hidden features we have not yet uncovered. Even the arrow of time finds new meaning here. Entanglement grows as systems interact. Once two particles collide, they remain correlated forever, their states entangled, even if they drift light years apart. Over cosmic history, entanglement has spread, knitting more and more of the universe together. This growth may be the reason time has a direction. The past is a state of lower entanglement. The future is a state of higher entanglement. Gravity, time, and causality may all be facets of the same unfolding network. The poetry of this vision is matched only by its strangeness. If ER equals EPR is true, then every particle in your body is connected by tiny wormholes to particles elsewhere in the cosmos. You are not an isolated being in empty space. You are a node in an infinite web of entanglement. The space around you, the floor beneath your feet, the stars overhead, are all woven from the same threads. The weight you feel pressing you to Earth is not a pull or a push. It is the emergent geometry of this invisible network, the way quantum connections bend into the shape we call space-time. And yet, we must be cautious. These are bold conjectures, not established facts. Experiments have not yet confirmed that space-time is entanglement, nor that wormholes and entangled particles are two sides of the same coin. But the mathematics is compelling, and the paradoxes that once seemed insurmountable dissolve when viewed through this lens. It is as if nature is offering us a glimpse of her hidden code, a whisper that beneath geometry lies information. What is most extraordinary is that this vision does not make the universe less real or less tangible. On the contrary, it deepens our appreciation. If space and time are woven from entanglement, then every orbit, every sunrise, every breath is the expression of quantum connections spanning the cosmos. We are walking on threads of information, living in a fabric of correlations, sustained by the entangled architecture of reality itself. The chapter closes here, but the story does not. For if space-time is woven from entanglement, then the cosmos itself may already contain evidence of this truth. The mysteries of dark matter, dark energy, and cosmic expansion may be not puzzles of missing particles, but clues that gravity is emergent. To follow these clues, we must look outward, to the largest scales of the universe, where gravity shows its strangest face. The story of gravity has taken us from Newton's falling apple to Einstein's curved spacetime, and further still into the quantum conjectures of entanglement. But the universe itself continues to challenge us with evidence that does not fit neatly into any theory. When astronomers look outward to the galaxies, when they measure the motions of stars and the expansion of the cosmos, they find puzzles that even Einstein's equations cannot explain. These mysteries are not hidden in laboratories or buried in mathematical speculation. They are written across the night sky. The first came in the mid-20th century, when astronomers began to measure the rotation of galaxies with precision. According to Newton and Einstein alike, the stars at the edges of a spiral galaxy should orbit more slowly than those near the center, just as the outer planets of the solar system move more sluggishly than the inner ones. But observations showed otherwise. The outer stars were moving far too fast, as if held in place by a gravitational pull much stronger than the visible mass could provide. The most natural solution was to assume there was more mass than we could see. This unseen mass was named dark matter, an invisible substance that outweighs all the stars, gas, and dust combined. Dark matter does not shine or absorb light. It reveals itself only through gravity, shaping the rotation of galaxies and the motions of galaxy clusters. Today, the evidence for dark matter is overwhelming. We see its fingerprint in the cosmic microwave background, in the distribution of galaxies across the universe, in the bending of light from distant quasars. And yet, despite decades of searching, we have never detected a single dark matter particle directly. This is a sobering fact. Entire generations of experiments have been built to capture dark matter, sensitive detectors buried deep underground to shield them from cosmic rays. Each time, the results come back empty. The universe tells us dark matter must exist, but our instruments remain blind. It is possible that dark matter particles are simply too elusive, interacting too weakly to be caught. It is also possible that the truth is stranger, that dark matter is not matter at all, but a sign that our theory of gravity itself is incomplete. The second great mystery is even more profound. In the late 1990s, astronomers measuring distant supernovae discovered that the expansion of the universe is not slowing down, as most expected, but speeding up. Some unknown energy is pushing the cosmos apart, accelerating the growth of space itself. This force has been called dark energy, and it appears to make up nearly 70% of the total energy content of the universe. Unlike dark matter, it is not clumped into halos around galaxies. It is spread smoothly across space, acting as a pressure that drives expansion. What is dark energy? Some suggest it is the cosmological constant that Einstein once introduced and later abandoned, a property of space-time itself. Others think it may be a new field, an energy that permeates the vacuum. But no one truly knows. Dark energy is invisible, untouchable, inferred only from the acceleration of galaxies. It may be the most important discovery in cosmology since the expansion of the universe itself, and it remains unexplained. These two mysteries, dark matter and dark energy, dominate modern cosmology. Together, they make up 95% of the universe, leaving the ordinary matter we are familiar with as a tiny sliver. If gravity is the architect of cosmic structure, then these unknown ingredients are the tools it uses, tools we do not understand. Their existence may be a clue that gravity is more mysterious than we thought. Perhaps our equations are incomplete. Perhaps space-time is emergent. Perhaps entanglement plays a role we have not yet recognized. What is certain is that the cosmos refuses to be simple. The more we look, the more gravity surprises us. It is not just the force that holds us to Earth or guides the planets. It is the shaper of galaxies, the driver of cosmic destiny, and the keeper of mysteries that may one day force us to rewrite physics once again. The mysteries of dark matter and dark energy have inspired an enormous effort to uncover their nature. But not all physicists are convinced they exist as substances. Some suspect that the evidence points not to missing matter or hidden energy, but to a flaw in our understanding of gravity itself. If Einstein's equations describe space-time as geometry, perhaps that geometry breaks down on cosmic scales. Perhaps gravity behaves differently in the vast reaches of intergalactic space than it does near stars and planets. One of the first attempts to question gravity came in the late 1970s, when Mordechai Milgrom proposed modified Newtonian dynamics, known as MOND. Instead of adding dark matter, MOND changes the law of gravity at very low accelerations. In ordinary circumstances, Newton's law works. But at the outer edges of galaxies, where accelerations are tiny, gravity becomes stronger than expected. This adjustment explains galactic rotation curves with uncanny accuracy, without invoking invisible mass. For decades, MOND was dismissed as a fringe idea, but it refused to die, because its predictions often matched galactic observations better than dark matter models. Critics pointed out that MOND struggled to explain phenomena on larger scales, such as the cosmic microwave background or galaxy clusters. To address this, more sophisticated theories emerged, like T-verse, tensor vector, scalar, gravity, which combined relativistic extensions with MOND-like behavior. These theories attempted to retain Einstein's elegance while explaining away dark matter. They have not yet succeeded fully, but they remind us that our laws are human constructs, provisional, always subject to revision. Another radical alternative has come from emergent gravity, proposed by Eric Verlinde. In his vision, gravity itself arises from the statistical behavior of microscopic information linked to entropy and entanglement. In this framework, the extra-gravitational pull we attribute to dark matter is not due to hidden particles but to the way space-time itself emerges. Verlinde's equations predict deviations from Einstein's theory that can mimic the effects of dark matter in galaxies. Though still debated, these ideas fit into the broader narrative that gravity may not be fundamental. Meanwhile, other physicists consider whether dark energy itself might be a sign of modified gravity. Perhaps the accelerated expansion of the universe is not due to an exotic fluid filling space, but to the failure of general relativity on the largest scales. Theories like F of R gravity modify Einstein's equations to include new terms, producing cosmic acceleration without invoking dark energy. In these models, gravity itself evolves with time, changing its behavior across cosmic history. None of these theories are yet proven. Dark matter still provides the simplest explanation for many observations, and dark energy still fits the data of accelerated expansion. But the persistence of alternatives reveals how unsettled the field remains. Gravity, so familiar in our daily lives, refuses to yield its ultimate secrets when stretched across billions of light years. What is striking is how these mysteries blur the line between observation and philosophy. Are we seeing evidence of unseen particles, or are we glimpsing the breakdown of our theories? The cosmos does not answer easily. It gives us data, and the data can be fit by many stories. The task of physics is to decide which story is true, whether through dark matter and dark energy, or through modified laws. The evidence points to one truth: gravity is not fully understood. Its role in shaping galaxies, in driving expansion, in balancing entropy and information, goes beyond what Newton or Einstein imagined. It may be that gravity is a window into the deepest layer of reality, a layer where space and time themselves emerge from quantum principles not yet revealed. The search continues, but the evidence already reshapes our vision. Gravity is not only a force that binds, it is a mystery written across the stars, a puzzle as vast as the universe itself. The universe has forced us to confront its mysteries not in hidden corners but on its largest scales. Dark matter and dark energy dominate the cosmic balance sheet, yet we do not know what they are. Modified theories of gravity promise elegant shortcuts, yet they stumble when tested across all observations. We are left in a strange position, where 95% of the cosmos is invisible and unexplained, or else our deepest theory of space-time needs rewriting. Both options are extraordinary, and both remind us how little we truly know about the force that has shaped our existence from the very beginning. This uncertainty is not a failure. It is a sign that gravity may be the doorway to a deeper reality. Every time gravity has confounded us, it has led to revolutions. Newton turned falling apples into universal law. Einstein turned geometry into the language of the cosmos. Quantum theorists turned entanglement into the threads of space-time. Now dark matter and dark energy may be pointing us toward the next transformation, one that unites the cosmic and the quantum in ways we cannot yet see. Consider what these mysteries mean for our place in the universe. The galaxies are held together by an invisible presence, whether it be unseen matter or emergent geometry. The expansion of the universe is driven by an unknown energy or by a failure of our cherished equations. Either way, the cosmos is telling us that the familiar is only a thin veneer. Beneath it lies a strangeness deeper than any fiction. And yet, despite this vast uncertainty, gravity remains the most intimate of forces. It is the pull we feel in our bodies, the weight pressing us to Earth, the cycle of tides that shape our shores. It is the bond that holds planets in orbit, stars in galaxies, galaxies in clusters. It is the architect of the large-scale structure of the cosmos, the hand that sculpts the web of matter across billions of light years. Whether carried by particles, encoded in boundaries, or emerging from entanglement, gravity remains the storyteller of the universe. But the cosmos has one more secret to reveal. For gravity does not only shape space, it also shapes time. Near massive bodies, time slows. In the depths of a gravitational well, the seconds stretch longer, the hours lengthen. The flow of time itself bends under gravity's hand. This is not illusion, but reality, measured with atomic clocks and satellites. To understand gravity fully, we must understand its marriage to time, its role in creating the arrow that guides all of existence. And so the journey continues. From Newton to Einstein, from quantum conjectures to cosmic evidence, we are brought now to the threshold of perhaps the most profound question of all. Not only why gravity exists, but how it is bound to time itself. To follow this path is to confront the most intimate mystery of the cosmos, the way gravity and time weave together to create the flow of reality. Of all the revelations born from Einstein's vision, perhaps none is as disquieting or as beautiful as the discovery that gravity shapes not only space, but time itself. Time was once thought to be universal, flowing at the same rate everywhere, a cosmic river in which all events were submerged. But relativity shattered this illusion. The flow of time depends on where you are and how you move. In the presence of gravity, seconds stretch, minutes lengthen, and clocks no longer agree. This effect is known as gravitational time dilation. Place two identical clocks in different gravitational fields, and they will not tick at the same rate. A clock on a mountaintop, farther from the center of Earth's mass, ticks faster than a clock at sea level. The difference is tiny, only a few billionths of a second per day, but it is real and measurable. Raise the stakes to more extreme environments, and the effect grows undeniable. Near a black hole, time itself slows to a crawl. To an outside observer, a falling astronaut would appear to freeze at the event horizon, their seconds stretched into eternity. To the astronaut, nothing feels unusual. Their heartbeat continues normally, their thoughts unfold in rhythm, but to the universe beyond, their time has diverged forever. This bending of time is not science fiction. It has been confirmed countless times in experiments with atomic clocks flown aboard aircraft, launched into satellites, or carried up mountain peaks. Global Positioning System satellites orbiting Earth must account for gravitational time dilation, or else their navigational signals would drift by kilometers each day. The corrections are not optional. They are proof that gravity and time are inseparable. The fact that gravity alters time is more than a curiosity. It means that the arrow of time itself is linked to the geometry of space-time. Wherever gravity bends the fabric, it bends the flow of time. This unites the ordinary with the cosmic. The seconds you live through on Earth are not the same as the seconds lived by an astronaut drifting in interplanetary space. The deeper you are in a gravitational well, the slower your time flows compared to the cosmos beyond. Consider what this means for the universe as a whole. Galaxies with supermassive black holes at their centers are not just shaped in space by gravity, but in time as well. The cores of these galaxies live slower lives than their outskirts. The cosmos is a vast mosaic of clocks, each ticking at its own rhythm, each shaped by the invisible hand of gravity. There is no single universal present, no master clock to which all events can be synchronized. Time is local, personal, tied to the gravity you inhabit. This realization forces us to rethink what we mean by past, present, and future. If time flows differently in different places, then simultaneity is an illusion. What is now for you may already be the past for someone near a massive star, or still the future for someone drifting far from all gravitational fields. Gravity does not merely shape the orbits of planets, it reshapes the very structure of time itself. And yet, for all its strangeness, this truth is woven into our daily lives. The phone in your pocket uses signals from satellites, corrected for gravitational dilation. Airplanes follow routes, guided by clocks, adjusted for both motion and gravity. Without these corrections, our modern world would not function. We live in a universe where gravity and time are intertwined, even if we rarely notice it. But the deepest implication lies not in our technology, but in the nature of reality. If time itself is shaped by gravity, then perhaps the arrow of time, the reason we remember the past but not the future, the reason entropy increases, is bound to gravity as well. Perhaps gravity is not just the shaper of space, but the very engine of temporality, the reason the universe flows. The strangeness of gravity's grip on time becomes clearest in the most extreme environments. Imagine hovering close to the surface of a black hole, near the event horizon, where escape is impossible. To you, time flows as it always has. Your pulse beats steadily, your thoughts unfold naturally, your ship's clock ticks second by second. But to an observer far away, watching through a telescope, your seconds stretch longer and longer. The closer you are to the horizon, the slower your clock appears. At the edge itself, time seems to stop altogether. You are frozen at the threshold of the abyss, never crossing from their point of view. This paradox illustrates something profound. Time is not absolute. It is not the same for all observers. It is bound to space-time's geometry, and geometry is shaped by gravity. The deeper you are in a gravitational well, the slower your time flows relative to the outside world. It is not illusion, but reality, measured in experiments and accounted for in technology. Even away from black holes, this effect shapes our universe. Consider the early cosmos, when matter was packed into a far denser state. Gravity's pull was immense, and the flow of time was correspondingly slower. As the universe expanded, gravity weakened on large scales, and time stretched out. In this way, the expansion of space is also an expansion of time. The story of cosmic history is written not just in distances and galaxies, but in the rhythm of clocks across billions of years. The arrow of time, the fact that we remember the past but not the future, may also be tied to gravity. The second law of thermodynamics tells us that entropy must increase. Systems move from order to disorder, from concentrated energy to diffusion. This growth of entropy defines the arrow of time. But entropy is inseparable from gravity. Without gravity, entropy would reach a dull equilibrium quickly, a featureless spread of particles. It is gravity that gathers matter into stars and galaxies, into black holes, whose horizons encode entropy in their surface area. Gravity ensures that entropy can grow in new ways, that complexity can emerge, that time has a meaningful direction. Black holes make this link undeniable. Their entropy is the largest of any object in the universe, scaling with their surface area. When two black holes collide, their horizon area grows, and their entropy increases. This matches the thermodynamic arrow of time. The growth of entropy and the flow of time are not separate phenomena. They are reflections of the same principle. Gravity is not only geometry, it is the sculptor of entropy, and therefore of time itself. This realization changes the way we see our own lives. Every second we live is not an independent tick of a cosmic clock, but a moment shaped by gravity's curvature. The arrow of time we feel in memory and history, in birth and death, is bound to the same law that guides stars and galaxies. We are not separate from the cosmos, but woven into it, our lives part of the same temporal fabric, shaped by gravity. Yet questions remain. Why should gravity be tied so deeply to entropy and time? Why does a black hole's entropy scale with its surface rather than its volume? Why does the growth of space-time mirror the growth of entanglement? These questions point beyond relativity, toward a deeper theory where gravity, time, and information are three aspects of one hidden truth. The evidence is clear. Gravity and time are inseparable. Without gravity, time would not flow as we know it. Without time, gravity would have no meaning. They are two sides of the same coin. shaping the universe together. But to understand why, we must look beyond Einstein's equations into the union of thermodynamics, quantum theory, and information. The union of gravity and time carries us to the edge of understanding. It is one thing to accept that clocks tick at different rates in different gravitational fields, or that satellites must adjust for dilation to guide us across the Earth. It is another to realize that the very concept of causality, the order of events, the chain of before and after, depends on gravity's shaping of space-time. Without curvature, without the warping of time, there would be no structure to the universe's unfolding. Gravity does not merely bend paths, it organizes reality itself. Everywhere we look, this truth is reflected. The merging of black holes creates not only ripples in space, but echoes in time, gravitational waves stretching and squeezing the very intervals between moments. The collapse of massive stars marks not only the end of stellar lifespans, but the reshaping of temporal order, as their interiors fall into regions where time slows, almost to stillness. Even the birth of the universe, the Big Bang itself, is not only a beginning of expansion in space, but of flow in time, an instant when entropy was at its lowest, and gravity set the stage for its relentless growth. The arrow of time is inseparable from gravity's influence. Entropy rises because gravity allows complexity to form. Clouds of gas collapse into stars. Stars forge elements. Elements form planets. Planets spawn life. Each step increases entropy, and each step is driven by gravity's pull. Without gravity, the universe would have reached equilibrium eons ago. A thin, uniform mist with no direction, no past or future, no story. Gravity is what prevented stasis. It is the architect of change, the silent companion of time's arrow. This link becomes clearest when we confront black holes once more. Their entropy, encoded on their horizons, grows inexorably. Their evaporation through Hawking radiation extends the arrow of time into the deep future, promising a cosmos where black holes slowly dissolve into radiation. The growth and eventual dispersal of these objects ensure that time continues to flow, that history has direction, even in a universe of dwindling stars. Gravity is both the sculptor and the witness of cosmic time, and so we come to a strange conclusion. To ask why gravity exists is to ask why time flows. They are inseparable mysteries. Gravity shapes time, and time gives gravity its meaning. The weight you feel, the pull of planets, the orbits of galaxies, these are not separate from the ticking of clocks and the unfolding of memory. They are one story, told in two languages. The geometry of space-time and the arrow of entropy are facets of the same truth. But that truth remains unfinished. We can measure, predict, and calculate, but we do not yet understand why gravity is bound to time in this way. Why should entropy scale with horizons? Why should the fabric of reality allow one direction of time at all? These questions point beyond physics as we know it, toward a deeper principle yet to be uncovered. The journey now circles back to the ultimate question. If gravity and time are two sides of the same mystery, then perhaps the reason the universe has gravity is the same reason it has history. Without gravity, there would be no stars, no galaxies, no life, and no time as we know it. The cosmos would not flow, and observers like us would never exist. Gravity is not only the stage on which time unfolds, it may be the very reason there is a story to tell. If we step back from the mysteries of black holes, quantum entanglement, and the bending of time, a simple question emerges. Why does the universe need gravity at all? It is tempting to imagine a cosmos without it, a vast expanse where matter drifts freely, unbound, never falling, never curving space-time. But such a universe would be sterile and lifeless. Gravity is not only the oldest force we know, it is the architect of everything familiar, the silent engineer of stars, planets, and life itself. Consider the earliest moments after the Big Bang. In that young, hot plasma, matter was nearly uniform, spread thinly across space. Without gravity, the tiny ripples in density would have remained ripples forever. No regions would have collapsed. No stars would have ignited. no galaxies would have spun into being. The cosmos would have remained a smooth soup of particles, cooling and dimming, but never producing structure. It was gravity that changed the script. Slight overdensities pulled in more matter, growing denser and heavier, their pull increasing as they grew. These collapses gave rise to the first stars, nuclear furnaces, where hydrogen fused into helium and heavier elements. Every atom of carbon in your body, every molecule of oxygen you breathe, every trace of iron in your blood was forged in a star's core, and it was gravity that made those stars possible. Without gravity, the periodic table would have stopped at hydrogen and helium. The chemistry of life would never have existed. Gravity does more than form stars. It binds them into galaxies, immense islands of matter spread across the cosmic sea. Within galaxies, gravity sculpts spiral arms and star clusters, orchestrates collisions, and creates the dense molecular clouds that give birth to new stars and planets. Every world we know, from the frozen moons of the outer solar system to Earth itself, exists because gravity gathered dust and rock into spheres, fusing fragments into planets. Even the conditions for life are written by gravity. Earth's mass holds its atmosphere in place, allowing water to remain liquid on the surface. The sun's gravity confines its nuclear fires, bathing our world in steady light and warmth. The moon's gravity shapes tides, stirring the oceans that may have nurtured the first life. On every scale, from the cosmic web of galaxies to the rhythm of waves on Earth's shores, gravity is the invisible hand that sustains existence. Imagine a universe without gravity. Stars would never shine, planets would never form, life would never awaken. Time itself might drift without direction, entropy collapsing into equilibrium too quickly for complexity to arise. A gravity-free cosmos would be silent, static, and empty of observers to ask why. In this sense, gravity is not only a force, it is the precondition for everything that matters, the foundation upon which complexity, history, and consciousness rest. This line of reasoning leads some to the anthropic perspective. Perhaps the universe has gravity because, without it, beings capable of asking questions would never emerge. We find ourselves in a cosmos shaped by gravity because only such a cosmos can host stars, planets, and life. This does not explain the mechanism, but it reframes the mystery. To ask why gravity exists may be to ask why the universe allows us to exist at all. And yet, even this perspective leaves open questions. Why does gravity have the strength it does, so much weaker than the other forces, yet strong enough to shape the universe? Why does it bind the cosmos on the largest scales, while leaving atoms and molecules free to dance in chemistry's delicate balance? The precise tuning of gravity seems almost uncanny, as though the universe knew it needed just enough pull to create structure, but not so much as to collapse too quickly. Gravity is not only necessary, it seems finely tuned, and that tuning may be the greatest clue of all, suggesting that gravity is not an accident, but a fundamental ingredient in the recipe of existence. Gravity's necessity becomes clearer when we imagine altering it. Suppose the strength of gravity was slightly greater. The clouds of gas in the early universe would have collapsed too quickly, forming stars so massive that they burned out in a few million years. Galaxies might have been smaller and denser, with frequent collisions and unstable orbits. Planets like Earth would never have had the chance to stabilize, and the long epochs required for life to emerge would have been impossible. The cosmos would have been a storm, brilliant but brief, collapsing into black holes before complexity could unfold. Now suppose gravity were weaker. Stars would have formed only rarely, if at all. Gas clouds would have drifted without collapsing, spread too thin to ignite fusion. The universe would be vast and dark, scattered with isolated clumps of matter, but never alight with stars. The heavy elements forged in stellar cores, carbon, oxygen, iron, would never have existed. Chemistry would have been limited to hydrogen and helium, simple and sterile. In either case, life as we know it would be impossible. The strength of gravity seems tuned to a narrow range, one that allows stars to shine steadily for billions of years, providing the energy for planets to nurture life. It is this balance that has allowed evolution to unfold, that has given rise to observers capable of reflecting on the universe's mysteries. But gravity does more than permit life indirectly. It governs the cycles of cosmic renewal. When massive stars reach the end of their lives, gravity causes them to collapse, igniting supernova explosions that scatter heavy elements into space. These elements seed new generations of stars and planets, ensuring that the universe is not static but evolving. Every breath you take contains atoms born in the heart of a star and scattered by gravity's hand. Without this cycle of creation and destruction, the universe would be barren. On galactic scales, gravity sculpts the large-scale web of the cosmos, the filaments and clusters that span billions of light-years. These structures are not only visually breathtaking but also essential for cosmic evolution. They channel gas into galaxies, regulate star formation, and provide the environment in which planetary systems emerge. Gravity is the architect of this cosmic web, weaving matter into patterns that set the stage for everything else. The delicate balance of gravity also explains why the universe has endured for nearly 14 billion years. If gravity had overwhelmed the expansion of space, the cosmos would have collapsed back into a singularity in a catastrophic big crunch. If it had been too weak, expansion would have carried matter apart too quickly, preventing galaxies from forming. Instead, gravity has held the universe in a balance, slowing expansion enough to create structure, but not enough to reverse it entirely. The cosmos is in a state that allows history to happen, that allows questions to be asked. When viewed this way, gravity is not just a force, but a condition for possibility. It allows stars to live long enough to forge elements, planets to orbit stably, galaxies to endure, and life to evolve. Its value seems written into the laws of nature with extraordinary precision. This has led some to wonder whether our universe is just one of many, each with different strengths of gravity, and we live in the one that permits us to exist. Whether or not that is true, the fact remains: without gravity, there would be no story to tell. This realization adds a layer of inevitability to gravity's presence. It is not merely one force among many. It is the background against which the entire play of existence unfolds. Strong enough to build stars, weak enough to allow complexity, persistent enough to bind galaxies, subtle enough to leave chemistry. Free gravity is tuned to allow a universe with history, structure, and life. The more closely we study the cosmos, the more gravity appears not only necessary, but inevitable, as though the universe could not be without it. Its quiet hand shapes everything from the vast structures of galaxies to the delicate balance that lets a planet like Earth cradle life. It binds the heavens together, yet it is so subtle that we can ignore it in the chemistry of atoms and the sparks of neurons. This duality, omnipresent, yet gentle, is what makes gravity unique. It is tempting to see in this balance a kind of fine-tuning. The force of gravity is weaker than the other fundamental interactions by orders of magnitude, yet its reach is infinite. It does not cancel out like electromagnetism, because mass is always positive. Gravity accumulates, one atom upon another, until its power becomes irresistible. It governs the universe, not through strength, but through persistence. Over time and scale, its influence is absolute. Some physicists turn to the anthropic principle to explain this precision. We find ourselves in a universe with this particular strength of gravity, because only such a universe can support observers. In a cosmos where gravity was stronger or weaker, there would be no stars, no planets, no minds to ponder the question. In this sense, our very act of asking why gravity exists is evidence that it must exist in this way. The argument does not provide a mechanism, but it underscores the deep link between the laws of nature and the fact of our presence within them. Others seek a more physical explanation, a theory that unifies gravity with quantum mechanics, revealing why it has the value it does. Perhaps gravity is not a fundamental force at all, but an emergent property of information and entanglement, as suggested by holographic models. If so, its tuning may be a natural outcome of deeper laws. What seems uncanny may be inevitable once the hidden structure of reality is revealed. What cannot be denied is that gravity is the architect of cosmic order. It transforms chaos into structure, turning random distributions of matter into galaxies, stars, and planets. It creates cycles of birth and death, forging the elements in stellar cores and scattering them across the cosmos in explosions. It balances expansion and collapse, allowing history to unfold across billions of years. It weaves together the story of existence, from the first light of the Big Bang to the galaxies that drift at the edge of the observable universe. In this sense, gravity is not only a physical force, but the foundation of meaning. Without it, there would be no stages upon which stars could shine, no worlds upon which life could awaken, no observers to ask questions. Gravity ensures that the universe is not an empty possibility, but a living reality, structured and evolving. It is the silent necessity that makes existence possible. And yet, the question remains, why does it exist at all? Why should matter curve space-time? Why should the geometry of the universe allow time to flow and structures to emerge? We know how gravity behaves, and we know what it makes possible, but the ultimate why still escapes us. This is the mystery that has haunted science from Newton to Einstein to the present day. As we stand at the edge of knowledge, one thing is clear. The universe needs gravity because we are here to ask why. Without it, nothing we know would exist. It is the condition for life, for history, for the arrow of time itself. And yet, knowing this does not end the mystery. It only deepens it. The final step of our journey brings us to this point. We can trace gravity from its role in stars and galaxies to its connection with time and entropy. But we still do not know why the universe chose this law. The question leads us into philosophy as much as physics, into reflection as much as calculation. Gravity is not just a scientific puzzle. It is the greatest mystery of existence. Gravity has followed us through every step of this journey. It was the force that first revealed itself to human imagination, the fall of an apple drawing Newton's thoughts toward the heavens. It was the invisible thread that guided planets in their orbits and pulled the moon across the sky, shaping tides that have marked time for countless generations. For centuries, we thought of gravity as obvious, as ordinary, the simple background of existence. And yet, the more we have studied it, the more mysterious it has become. Newton gave us the law of universal gravitation, a description of how every mass pulls on every other. With his equations, humanity could predict the motions of worlds, launch ships into the sky, and calculate eclipses centuries in advance. But Newton himself admitted that he did not know what gravity was. He described its effects with elegance, but its cause remained a mystery he would not claim to explain. Einstein offered a new vision, one so audacious that it redefined reality itself. In general relativity, gravity was not a force acting at a distance, but the curvature of space-time. Mass and energy bend the fabric of the universe, and objects move along those curves. The predictions of this theory were stunning: light bent by stars, clocks slowed by gravity, ripples in space-time, radiating from cosmic collisions. For over a century, experiment after experiment has confirmed Einstein's vision. Gravity is geometry. Space-time is alive with curves and waves. And yet, Einstein's triumph did not end the mystery. It deepened it. If gravity is geometry, why does matter bend space-time? If time slows near mass, why should time itself be tied to curvature? If gravity is the shape of reality, what sets that shape in motion? Relativity explains how gravity works, but it still leaves unanswered the question of why. The quantum revolution brought new puzzles. Every other force of nature fits within the framework of quantum field theory, mediated by particles and described by probabilities. But gravity resists. The hypothetical graviton has never been detected, and the mathematics of quantum gravity spirals into infinities that defy resolution. Attempts to unify gravity with the other forces through string theory, loop quantum gravity, or holographic dualities have offered glimpses of possibility, but no final answer. Gravity remains apart, a loner among the forces, immune to the neat unification that science craves. Then came the suggestion that gravity may not be fundamental at all, but emergent. The holographic principle showed that space-time itself might be encoded on boundaries, like a projection from lower dimensions. Entropy and information pointed toward gravity as a thermodynamic phenomenon, a side effect of quantum entanglement. In this vision, gravity is the tapestry woven from connections, not a thread of its own. Meanwhile, the universe whispered more mysteries. Dark matter, unseen but undeniable, pulling galaxies into shapes that visible mass could not explain. Dark energy, driving the cosmos apart with a force we cannot comprehend. Modified theories of gravity, bold attempts to rewrite the equations that Einstein left us. Each clue added weight to the mystery rather than clarity. Through it all, gravity has remained the stage on which existence unfolds. It is the shaper of galaxies, the sculptor of stars, the keeper of time, the architect of possibility. Without it, the universe would be featureless. With it, the universe is alive with structure, history, and wonder. And yet, for all its power, we do not know why it exists. This is the paradox at the heart of science. The more deeply we understand gravity, the more profoundly it resists final explanation. It is as if the universe has given us the rules of the game, but not the reason the game is played. Gravity holds a strange position in human thought. It is at once the most familiar of experiences and the most elusive of mysteries. We feel its pull every moment of our lives, in the weight pressing our feet against the ground, in the arc of a stone tossed into the air, in the rhythm of tides that sculpt our coasts. Yet when we search for its essence, it slips beyond reach. We can measure its strength with exquisite precision, yet we cannot grasp its origin. It is the simplest of forces to describe and the hardest to explain. This tension gives gravity a unique role in the story of science. Every advance has sharpened the mystery rather than ended it. Newton gave us equations that unlocked the heavens, but not an explanation of why mass attracts mass. Einstein revealed gravity as geometry, but not why geometry itself should exist. Quantum physics revealed entanglement and holography, but not why space-time should emerge from them. The more we illuminate, the more shadows appear. Gravity has always been the teacher who answers one question only to pose another. Perhaps this is why gravity feels almost philosophical, even spiritual, in its presence. It is not simply a mechanism, but the condition for existence. Without it, there would be no stars, no planets, no life. The universe would be an empty haze, cooling toward nothingness. Gravity turns possibility into structure, potential into history. It is the difference between silence and song. And yet gravity is not overwhelming. It is the weakest of the fundamental interactions, feeble compared to electromagnetism or the nuclear forces. A small magnet can lift a nail against the pull of Earth itself. And still, because it never cancels, because it only adds, gravity dominates the cosmos on the largest scales. Weakness becomes strength through persistence. Over time and distance, it shapes galaxies, bends light, and molds the fate of the universe. This paradox of weakness and dominance is part of gravity's poetry. It does not force itself upon us with violence. It guides gently, persistently, invisibly, until everything bends to its will. Stars burn because gravity holds them together. Worlds orbit because gravity choreographs their paths. Even time bows under its influence, stretching and slowing where mass is great. Gravity does not merely act within the universe. It shapes the universe itself. Some imagine that one day we will solve the riddle. A final theory will reveal why gravity exists, uniting it with the quantum, showing us the hidden code of reality. Others suspect that gravity is not meant to be explained in that way, that it is a principle as fundamental as existence itself, a truth that cannot be reduced. Whether it is particle or emergent phenomenon, geometry or entanglement, law or inevitability, gravity may be the deepest expression of the universe's being. But perhaps the most profound truth is this: gravity is not only what holds the cosmos together, it is what holds us within the cosmos. It binds us to Earth, to the sun, to the galaxy. It binds our history to the history of stars, our atoms to the cores of long-dead suns. It is the thread that links us to everything that ever was, and everything that ever will be. Gravity is not just physics, it is belonging. It is the bond that ties us to the universe and reminds us that we are not separate, but woven into the same fabric of space-time and time itself. From the first apple that fell into Newton's thoughts, to Einstein's vision of curved space-time, to the quantum conjectures that space-time itself may be woven from entanglement, gravity has been our most faithful companion and our most unyielding enigma. It is the force that guided us into the scientific age, the thread that pulled our imagination outward to planets and stars, and the puzzle that continues to challenge even the most advanced theories of modern physics. We have learned much. We can describe gravity's action with laws of extraordinary precision. We can predict the dance of planets centuries in advance, calculate the bending of starlight, measure the ripples of space-time as black holes collide. We can even account for its influence in our daily lives, adjusting clocks on satellites so that navigation systems remain true. We can describe and we can calculate. But describing is not the same as understanding, for beneath every explanation lies the unanswered question, why? Why should matter curve space-time? Why should the geometry of the universe bend light and slow time? Why should the cosmos have this force at all, so weak in the laboratory, yet so absolute across galaxies? Why should entropy and information be bound to it, as though gravity were the grammar of reality itself? These questions remain, persistent and profound, refusing to yield to equations alone. Some believe the answer lies in quantum gravity, in a yet-to-be-revealed union of relativity and the quantum world. Others think gravity is emergent, the large-scale appearance of entanglement and information, not fundamental but inevitable. Still, others suspect we are missing a principle entirely, something deeper than geometry or particles, something that will redefine physics once again. We stand, as Newton once did, at the edge of mystery, able to see the law but not its source. And perhaps that is the true gift of gravity. It reminds us that science is not only about answers but about wonder. Gravity holds us to Earth, but it also holds us to the questions that make us human. It keeps us searching, doubting, reaching, never content with the obvious. It is the force that binds the universe, and the mystery that drives our curiosity. In the end, gravity is not just a force, it is the stage upon which existence unfolds, the script written in the curves of space-time, and the thread that ties the story together. It shapes the cosmos, it shapes time, and it shapes us. We can measure its pull, but we cannot exhaust its mystery. So when we ask, why does gravity exist? The universe answers with silence and with stars, galaxies, and the flow of time itself. Perhaps that silence is the truest answer. Gravity is not merely something the universe has. Gravity is what the universe island, the deepest riddle, the oldest force, and the mystery that holds us.